Welcome to the General Chemistry Laboratory. In this first experiment, called Intro, you will be introduced to the use of balances for the measurement of mass. There are many different types of balances. And in this course, you'll be using at least 4 different types throughout the semester. In science, we use the metric system for making measurements. Now, the unit of measurement for mass is called a gram. Now, also remember that the metric system is a decimal system, so that there are other units such as a kilogram, which is 1,000 grams, and a milligram, which is 1,000th of a gram. Haven't got a clue about what a gram is? Well, reach in your pocket or purse and pull out a nickel. The nickel, first minted in 1866, was created by Congress to be a 5-cent piece made of a copper-nickel alloy and to weigh exactly 5 grams. One of the first official metric items ever to be manufactured in the United States. Although we frequently use the terms weight and mass interchangeably, they are actually quite different. The weight depends on the force of gravity, so that where you have high gravity, you will have a higher weight. Where you have low gravity, you'll have a lower weight. Whereas mass is constant. It is an intrinsic property of the matter itself. Now, for example, if you go into outer space, you become weightless, yet you do not change your mass. Here on Earth, because the Earth is an oblate spheroid, as you go from the North Pole to the equator, or if you go from sea level to a mountain peak, the force of gravity goes down and therefore your weight will go down. But remember, your mass remains constant. Instruments which measure mass or weight of materials come in many sizes and shapes, but they can be categorized in several different ways. They can be categorized by how accurately they weigh. They can be categorized by the principle that they use in making a weighing, or they can be categorized by the capacity that they can weigh. In our lab, we will be using balances which weigh to 100th of a gram or even a milligram here. But one of the most important balances you'll be using is one which will weigh to 1/10th of a milligram. That's 0.0001 grams, 4 decimal places in grams. This is called an analytical balance. So if you're told to weigh using an analytical balance, you are expected to get 4 decimal places in grams. Or if you're told to weigh with an accuracy of 0.1 milligrams, then again, you must use an analytical balance. There are other balances even more sensitive. If they weigh a microgram, those are called microbalances. Balances can also be categorized by the principle by which they work. Classically, we have mechanical balances, such as the scales of justice, where you have 2 pans. On one pan you put the crime, and on the other pan you put the punishment, and the two should balance out. In the case of making a weighing here, we put the object to be weighed on one pan, and we put weights on the other pan to balance it out. Remember, this is sort of like a teeter-totter, and in addition to just putting weights on, you can also move in or out away from the fulcrum with these weights, so that you can get weighing by either adding more weights or moving the weights further or closer to the fulcrum. Now, modern balances, the ones which you mainly see today, are called electronic balances, and they differ from these mechanical balances only because they do not use weights to balance out. They use an electrical current, so that what you are measuring is an electrical current needed to restore the balance to its equilibrium position. And finally, if you go to your bathroom, you probably have a scale there. This bathroom scale is not called a balance, it's called a scale. It is not as accurate as balances, but it works on the basis of a spring. The spring extension can be calibrated with the differences in mass. Finally, balances can be distinguished by the capacity of the balance. That is, you expect to see a different balance in the laboratory where you're weighing just a few grams or 100 grams relative to weighing a truck filled with gravel. With that introduction, it's on to our feature presentation, the balances which we will actually use in our laboratory. Probably the most important balance you'll be using this semester is the electronic analytical balance. Now remember, this is an analytical balance and it weighs to 4 decimal places in grams. Now to use this balance, now notice it's enclosed in glass here. That's because it is so sensitive that air currents will affect its reading. So make sure that this balance is closed. Then make sure that the balance is level here. You've got the level here, it's a bullseye with the air bubble right in the middle of the bullseye. And then make sure to start out with nothing on the pan. It reads exactly 0.00. And to do that, you press the 0 tare button here. And now it reads 0. You open the door, put the material to be weighed on the pan, close the door, make sure the door is closed when you're making these readings, and you weigh the material and read out 46.5333 grams. So here's a close-up. As you can see, here's the reading, 46.5331. It'll vary slightly in the last decimal place here. You notice here that the bubble is right in the middle, so the balance is level. And these are the zeroing spots here on this particular balance. If you weigh cylindrical objects, long cylindrical objects, any cylindrical object though, make sure you put them on these 2 little dimples in the pan. And then the other thing is make sure that you have set the object so that it will not touch the side of the balance. You will not get a correct reading if the object is touching the side. Do not use regular paper in weighing out powders on this balance. There is something called weighing paper, which is used for analytical balance. It has a very slick finish. But regular paper is much too porous, so if you weigh out something very accurately here, you probably will be unable to transfer it without losing some due to the porosity of the paper. Never weigh hot objects on an analytical balance. The closed container will set up convection currents of the heat rising and falling, and this will make the object appear to weigh too little. Furthermore, the object will change weight with time. Finally, make sure that you keep the area around all balances and the balances themselves very clean. This goes for all balances. Now, as far as the electronic analytical balances, they are very convenient to use, but they are sensitive and should be used only for the most accurate measurements which are required by the experiment. Your manual will tell you when to use them. Another very useful balance is the triple beam balance. It is not as accurate as the analytical balance. This particular balance only at best will weigh to 1/100 of a gram, 0.01 grams, but it is a very rugged and easy to use balance. Remember, whenever you weigh something, you really have to make 2 weighings. On the analytical balance that we just saw before, remember, you first of all made sure that it read 0. That was your first weighing, the 0.000 weighing. And then you made the weighing, and so the difference between those 2 weighings was the weight of the flask. Here again, you have to make a weighing. And if you're just weighing a flask, for example, what you must do is you must set this to 0 over here. To set it to 0, you adjust with this knob here. Now, one other possibility is that if you can't get it to 0 or don't want to get it to 0, you make a mark over here, as you see some people have done, where it does level out where it comes to equilibrium. Then when you make the weighing, you bring it to the same mark. Well, here we have it pretty well set to 0, maybe just a little higher. So now we'll put the object to be weighed on the pad. And we make sure, of course, that all of these weights on the beam here are at 0 to start. We start out with the highest weight. It must go into the 100 gram notch. And as you can see, it is too heavy now. This beam has gone down. So we bring the 100 back, and now we start moving to 10 grams. This is 10 grams, 20 grams, 30 grams, 40 grams, still not enough. We go to 50 grams, and now you see it is too much. So we go back to the 40. Finally, when we want to get the exact weight, we use this third beam now, which is a continuous beam, and we move this slide over until we get back. This gets right back to where it was when we started here. Here's a close-up of that reading. It's in the 40 notch, so that's 40 and 5, so 45.89 grams. Notice this balance differs from the electronic analytical balance in several different ways. One, it measures only to 2 decimal places in grams, and the other is it uses weights to balance it out again. If you want to weigh a powder on the triple beam balance, what you will need to do is weigh it on a piece of paper. Now remember, when you're weighing something, you actually have to make 2 measurements. We have previously zeroed the balance as our first measurement and then weighed the material on the balance. This time what we'll do, instead of zeroing the balance, it's not quite 0, it's a little bit below. What we'll do is put the paper on the balance pan and then zero it. And we get this back. And so now we have the paper and the balance reading 0 with the paper on it. We will weigh out 1 gram of our powder, so we will move this dial 1 gram. It was at 1.00 before, now it's at 2.00. And now we will add the powder that we're weighing out. We're weighing out 1 gram. And as you can see, use a rolling motion here. Tilt it, the bottle slightly, and then use a rolling motion. We're just about there. And a few more. And if you go slightly over, what you can do is take a little bit off and then throw the rest of this away. Remember, when you're through with the balance, get rid of and throw away all the waste material. A balance very similar to the triple beam balance that you just saw is this top loader balance. It is an electronic balance, but it weighs to 2 decimal places, much like the triple beam. But it is also much easier to use. Again, as in any weighing, make sure this goes to 0 to start out with. This is actually weighing now to 1 milligram. Then put your object to be weighed, and it reads directly. And again, remember, this is not weights balancing out the mass of this object. This is an electrical current balancing out the mass of this object. And you can read it right there, 46.49 grams. Finally, on a couple of occasions, you will use a mechanical analytical balance. Now, this is an analytical balance, which means it weighs to 4 decimal places. It is a mechanical balance, which means that it uses weights to counterbalance the object being weighed. The weights in this balance are in the top part here, where these are the weights, and they are dialed up by the dials which you have on the balances here. It is an obsolete balance, and it is fairly complicated to get started, so it probably is better if the instructor shows you how to use it. So see your TAs when you need to use this balance. In this experiment, you will also measure the mass of a U.S. penny, which will be like one of these. Heating one of these in a flame makes it red hot. Now, heating the other in the flame, what's happening here? What's happening here? Whoops. Well, what's happened? I'll let you figure that out.